My name is Shayon Sanyal. I'm a principal database specialist, work at Amazon, AWS. And I do have a copy of these slides, but if you do need it, I cannot share it just on a public website. So please feel free to email me or connect with me on LinkedIn, and I can share this with you directly. So just so it has the trademark and the copyright stuff, I cannot post it directly online, but I can share it on a one-on-one basis. So this talk is called JSON and Postgres, Learning with a Case Study. And the previous talk kind of set the stage where Ryan touched upon a little bit about the power of Postgres with non-relational data types, especially arrays, JSON, JSON-B, so on and so forth. So this is the agenda. This is, again, a very introductory talk. This is not supposed to be super advanced, very complex. This is more or less there to help you get going and really pick up on the power of JSON. This is something I used myself. I work a lot with my customers on a day-to-day basis. These are typically financial services, so they will use a lot of these NoSQL style querying in the relational databases. So anytime you have like a Postgres production instance or a deployment, you basically are looking to expand that to support newer use cases with non-relational. This is where JSON can be a very handy skill set to have. So we'll cover some basics about JSON, nothing new about it. We'll see the evolution over a lot of Postgres versions historically, where it was, how it has evolved, and where it is today. We'll see some basic examples. I, of course, have some screenshots captured, and some of them may be a little small given the font size, etc. So I encourage all the backbenchers to please kind of come forward if you really want to see those examples. Then we'll see JSON path, which is sort of an advanced JSON syntax to query a lot of your JSON or JSON-B data types within Postgres. We'll look at indexing, which is actually one of the really cool features to help with performance, especially on JSON-B. We'll look at gin, we'll look at B-tree, etc. And then some anti-patterns and wrap it up with some closing thoughts. So this is where we sort of see the segregation of choosing a NoSQL database versus going NoSQL with Postgres. Right, so hopefully I am able to clear a lot of questions, but if you do have questions along the way, please hold them until the end, and we'll take them towards the end when we have 15 minutes for Q&A. So this is, what is JSON? JSON is nothing but it's a JavaScript object notation where it's a very flexible format, similar to how you use CSVs today. You can port it to any system. You can export it out to flat files. You can export it out to object storage like S3, etc. And just instead of rows and columns, it just stores these values in key and value pair order, right? So that's basically what it is. Very flexible. Virtually, you can use this with any programming language, Python, C, C++, etc. And the graph here shows the popularity in the open source community, right? So JSON has picked up really, really fast, and more so in the recent years. More so in the millennial sort of generation. So if you look at, compared to like CSVs or XMLs or YAMLs, it's basically their popularity is just going down, and it just speaks volumes about the popularity and the ease of use JSON provides even within Postgres. Right? You'll see how easy it is to pick it up. So this is the example we'll walk through pretty much towards from here on to the end, and this is a very simple example of just a simple lunch order by a student in a school. It has the student ID. The first value, of course, is a key. The following value is the value. And then you have key value pairs, and you can have nested values. You can have arrays. You can have indexed values or indexed elements, etc. And we'll look at all those use cases in greater detail as we walk along. But this is a simple student with an ID 100. He bought some lunch at his school, which consists of an entree. It has a couple of sides. It has a snack, right? Very simple. So this is the evolution. Hopefully, the font is not too small. But 9.2, with Postgres 9.2, this was when JSON was first introduced. So it goes way back, 2012, almost 11 years, where it first came up in Postgres. It made its appearance. So it's not new. It has been there for quite a while, and it has evolved quite a lot over time. 9.4 release, Postgres 9.4 actually saw support for JSON-B, which is a binary version. There is a conversion included there, so JSON is converted to JSON-B format, which is where this is a little inefficient in terms of storage. But then the benefit is it supports indexing, which really performs very fast for your queries. Especially more, you'll see these use cases with, if you have use cases like full text search. So you can have GIN indexes on your JSON-B columns to help facilitate that. Of course, with JSON introduction in 9.2, what you were doing was storing these blocks of text with all white spaces, et cetera, in your database. That's where it was a little inefficient. It gave you the ability, but then it was lacking the maturity and the sophistication to trail or eliminate those white spaces. So JSON-B did that with 9.4. And later in 2019, with Postgres 12, this is when JSON path was introduced. This is more of an advanced JSON query format where you basically can have all the operator support. Let me look at what operators JSON supports today. Plus, you can also do key value lookups and full text searches within JSON path with a couple of operator classes that we'll look at. So given that sort of historical evolution, of course, there's a lot that is being added every feature release, every major release. And this is sort of the example we'll walk through, right, to demonstrate the power of JSON. So this is the way you would store this value in a Postgres table is exactly how you would store any other value, right? You don't want to think about JSON as its completely independent entity, standalone, very special class. This is exactly how you would store, let's say, a big int or a dint, how you would store a char or a varchar. So you pretty much define your table. So create table lunch orders, and just change the data type to JSON. So here you have a simple table with student ID, which is an integer type, and your order, which is a JSON. Then for the inserts, it's exactly the same. Instead of just the varchar value in double quotes, you're basically just putting it into those curly brackets and putting the whole block of text or that document in the table itself. So insert into this table values, your integer, followed by the block of text. This is your document. So I've inserted a couple of rows in that table for this student, for the same student. How this would look like is this. So you have a document now thrown into your relational database. Similarly, this is exactly how you would also see if you use something like DocumentDB or MongoDB or DynamoDB. If you query those databases, this is exactly how you would see it. The storage will be a little different. The representation will be a little different. You are basically there creating indexes, secondary indexes, and searching by API calls, querying on specific keys, et cetera. But this is how you would do it relational in a relational database like Postgres, just like any other data type, right? So this is the boring aspect of it is actually the most important one because it just works, right? That's the beauty of it. And then you have the JSON-B type, which is the binary representation. The only thing different here is JSON-B as the data type. That's it. Other values are exactly the same. So how would it look like? It would look like exactly the way it would look like when you're storing a JSON document in your relational database. So let's look at the operators. So this is where we add on to the array sort of functionality, right? So operators, more operators supported with JSON types and JSON-B types compared to the arrays. So this is where you actually build on those capabilities. Starting off with the first one is sort of, we call it the arrow, the single arrow. The second is your double arrow. So it's lack of a better word, it's basically just that. It's the single arrow operator and the double arrow operator, where you get these operators to do all sorts of querying, all sorts of filtering, all sorts of full text searches for your document store, document style data values, right? So the first four are actually JSON and JSONB supported operators. And the last two are the ones where you do your full text search with just JSONB types. And these are more sort of, there are a lot of variants to these. There are more operators than this. This is just a subset where you can have the return types as either integer or text, which is basically you can have an array, the indexed array value return, or you can have an object, the full element return from that array. So this is where it builds on the array data type that we saw in the previous session, where this expands the power of non-relational in the relational database. So a couple of examples. How do you query these? The table that we just created. So let's say I want to find all days that a specific student bought their lunch. So what I can do is the single arrow operator here. So this will query your specific days. So this is exactly same to how you would use your SQL query just with a where clause. Just because you have order date as one of the nested values in your JSON type, that's where you have the single arrow. So order consists of order details. It consists of order date. It consisted of cost. So you're just querying on the order date type here. The other example would be filtering. So just similar to your SQL queries, here you have the double arrow operator. Right? So you're querying your document stores now with your double operator with a very specific value. So your predicate is your date type. Again, since you have a multi sort of dimensional JSON document, you have order date, you have cost, you have this student ID and the order details. All you need is the order date to be of a particular value, and that's how you just query that out. How do you get data from a specified array? So this is where you would use something called as a chaining of these single arrow operators. So you have two arrows going one after the other, and basically your order details consisted of an entree, it consisted of a side and a snack. So within the order detail, all you need is the side value. So you'll just query on the sides, and you'll get those values out. Right? So it's super powerful. You can build on these examples to kind of grow the story even more. This is the other way to do it, where now you can actually have an array index. The way this is a little bit different from arrays in Postgres is JSON does have 0 as its starting position. Right? So arrays, you saw 1 as your starting position. With JSON types, you can actually have 0. So here, if I want to query just the first side that I ordered, for example, it was Apple for the example that we had, here you will just query the array index. So this is your array index here, 0, and you can just get a single side out of it. Right? So this is super powerful because if you think about it programmatically, you can very easily just have your Python script or your ORC or your ORM framework just do these index-based searches and lookups, which is much more efficient compared to a full text. Right? The other example is find every side dish students have ordered. So this is, instead of chaining now, this is the alternate way to do it, where you can have this ampersand arrow format. This is another operator that you can use to get exactly the same data out, but much easier, right? You don't have to specify multiple chains because you now don't have to spend that much cost in planning that query. So this is much more efficient, much faster in terms of query execution times, as well as the plan, right? So this will be much easier for the optimizer to look at and retrieve. This is checking if a JSON object contains a value. So this is now you are looking at specific values within those 3D rows, right? So your 3-dimensional arrays, 2-dimensional arrays. This is where it starts getting different from the array data type. This is where you can find specific values, you can filter for those, you can query those, and get it up, right? So this is your full text search sort of scenario. So the way you do this is, again, with your ampersand operator. And basically, you have that value specified within the array element. So within order details, if I had a side of salad, This is similar to an any sort of a keyword functionality. So you'll find all the rows that have your salad keyword present in them, right? Now we go on to the little bit of an advanced sort of a syntax with JSON path. This is where you have much more than what JSON-B offered or arrays offered. Dot can be used for member access, similar to how you do it with your array indexes. Square brackets are used for array access, so similar to the examples that we saw. But the beauty of this is you actually get a lot of built-in functions. This is just one example where you can actually get the size. This is a size function where we are checking every order that had at least one snack. So the way you do this is just query your database with your order details .snacks.size. So snacks is the sort of sub-element that we want to check the size for. And as long as it has one snack as its element, it'll retrieve those values. Similarly, there are other functions. A lot of those are not here. So there's quite a lot of documentation around this as well. So the next one is comparison without typecasting. One thing JSON sort of lacked back in the day was anytime you have a data type like numeric or float, and you have these sort of value comparisons or things that you just compare it against. So let's say your order detail cost is greater than a certain number, 4.5 or 5.6. Anytime you have that in JSON, because of the complications underneath in the storage system, subsystem, it does have to be converted to that specific data type to even perform that comparison, right? So with JSON path, that is no longer the case. So JSON path is this, whereas in JSON, previously you had to convert this or typecast this explicitly into a numeric data type first, just to perform that conversion. And that is super operationally expensive, right? So converting any data type from either like a big int or an int to a numeric or a char is expensive because of all sorts of computation issues. And this was used to be the case. This used to take forever to run, the query below. And the query above is now sub-milliseconds. This is like 0.5 milliseconds or something that we're talking about. So a lot of efficiencies with JSON path, just the way it's implemented under the hoods. So that's a very quick summary of some of the operators that we saw. There are tons and tons more, but we saw the single arrow, we saw the filtering with double arrows, we saw selecting nested values using ampersand, and then checking array elements, individual array elements with ampersand arrow. And then you have JSON path, which is sort of the big boss, the extreme end of JSON, right? That's like the superpower, JSON on steroids kind of a function. Now the beauty of JSON-B types, right? So indexing. This is sort of the highlight. This is a real story of a lot of customers where they are using this for full text search against something like Elasticsearch altogether. And this is sort of super powerful, and you'll see why. So there are more. Postgres does offer 3 types of indexes to work with JSON, but there's more being added. Of course, first being the B tree, which is the basic index type. Then you have the GIN index, which is primarily used for full text search index. And then you have the hash. So this is a lot less used. At least I have not seen that much of a use, especially with JSON types. But in regular usages, your hash index is very, very powerful. So we have a similar table. So we'll take the same table of a lunch order from the student. And we'll see that if we run this query as is, without any index, this is what you'll see. Of course, a sequential scan. You have full table scan going in, a very expensive operation. So what I did was create this benchmark. We did this with like 1 million, 10 million, et cetera. Just for simplicity, I've kept it to 1 million in this use case. I have a simple table with an ID, which is a big int, and a val, which is a JSON-B type. It has your 1 million sort of rows. And the structure is something like this. So you have an ID, which is a big int. Val is a JSON-B array with different data types. So you have the first value as your just a random generated value, JSON versus JSON-B test1. Val2 is a simple integer. Val3 is a date type. Val4 is an array, right? This is like an indexed array with 3 elements. So with the unindexed table, with a 1 million row unindexed table, it takes about, I hope you can see this, this is in red. This is about 86 milliseconds, give or take, which is still not bad, right? So this is just the hardware. This is, I did this on, of course, Aurora. This is Postgres 14.6. It is an R6G2XL, so this is a Graviton type with certain CPU memory, not as much. It's like a 32 GB memory with about 8 cores. And this is sort of the explain analyze on that query. So this is just an unindexed table. It takes about 86 milliseconds, right? Also does a sequential scan. So 2 things out of the bat, really bad. Now, do you see one more critical difference here? If you look closely, can someone point out what that key difference is? I'll give you a couple of seconds to look at it. Sorry? OK, that's one. Yeah, it's a good catch. What about the actual row count and the estimated row count? Do you see any difference? So you see about 11,000 in your actual row count, whereas you see about 2,083 in your estimated, right? It's way off. So
I found this on the web.
What about statistics, right? I was Siri going bonkers with JSON-B. Sorry. So one thing to note with JSON-B data types, or even JSON, is Postgres does not collect statistics on these columns, right? So even though it helps you with expanding your document use cases on your relational databases, queries will be really good. Your full text search queries will be really performant. But then don't trust it at the face value of an explain plan. Your explain plans will always be off, right? They will never be accurate in terms of the number of rows, actual rows returned versus the estimated row count. Because of the fact that you have these underlying sort of different ways of storing the JSON-B data as a binary representation, and because of the fact that it just actually calculates 0.05% cardinality of the table. So it's a very small number, and that's the number that you see. It's like of the overall number, the actual row count is just 0.05%. That's the value it will calculate stats for. That's it, not beyond that. So forget about that for a second. Let's focus on the execution time and the plans, right? So let's now create a B-tree index. This is a simple index, basic index. You just create it like any other. Create index, blah, 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 index name on the table type. And then we are creating this on val3. Note that val3 is, I think it's a date type. So we'll query this and see the difference. But you created this index, and then you did an explain analyze. And you're searching for that specific date value. You see the 86 milliseconds drop down to 28 milliseconds now. Right, so B-tree is super powerful. You'll see the sequential scan just go away. There's a bitmap index scan. You have your index condition there highlighted. You still see the rows are off. They're still close, but they're off, right? So 5,000 against 33,000, still very off. So you don't want to look at those when you're looking at JSON-B columns in your database. Look at the execution time, look at the indexes, whether they're being used or not, and that's like indicative of how better your performance is getting with JSON-B types or JSON types. So we are happy with the 20th millisecond. Now let's go even further, right? So GIN index. This is sort of a real use case where you have full text search capabilities with JSON-B types within Postgres. So GIN is, just a quick refresher, it's a generalized inverted index. So used for efficiently searching keys or key value pairs within this whole blob of a document. You can very quickly and very easily just parse the specific index array element and get values out of it, exactly how you would do it via a search engine, like an Elasticsearch. So it does support two operator classes, JSONB ops, which is the default, which provides you indexing on each key and value in the JSONB document against JSON path ops, JSONB path ops, which just indexes the values in your document, JSONB document. There is a few differences on the operator support for both JSONB ops versus path ops. So ops will support a little bit more of the operators because it's just simpler to operate. And your path ops has a limited sort of set of operators that can work with it. The other thing with path ops is as it'll be a little indicative of the name, it actually traverses the entire path of the plan. So it's a little bit slower. It basically does a full index scan compared to like a bitmap index or something else. So it's a little bit slower. And if you have a larger document, I would not recommend using JSONB path ops, but use the JSONB ops class of operators to operate on your full text search use cases. So in terms of the size difference, I created sort of two indexes. The first one is using JSONB ops, which is the default. And the second one is using path ops, which is the slower one. You'll see the difference in the size is actually your path ops is smaller, and your JSONB ops is actually a little bit bigger. Difference isn't too much, but can really change if you have really large documents to store, right? Now let's create these indexes. So let's create a GIN index on our val4, the column that we've been testing. And then if we run an explain analyze using our, this is your a regular GIN index. This is not using JSONB ops or JSONB path ops. By default, it will just implicitly call JSONB ops operators. And therefore, you see some sort of an inefficient execution time. You still see 77 milliseconds, which isn't that bad. We are getting there, but we are not quite there yet, right? So GIN introduced something called Trigram indexes. So there is another class of indexes for full text search, which is where they use PG Trigram module. This is a contrib library that provides these specialized functions and operators for determining your similarity of alphanumeric or text-based pattern matching. So you can use regex expressions, you can use regular expressions, or just pattern-based matching like wildcard expressions for your full text search use cases. And it supports the GIN Trigram ops operator class that gives you these sort of capabilities, right? One thing I'll highlight about JSON or JSONB is you don't really need any sort of extensions. You don't need any sort of contrib modules to be installed. If you're coming to like from open source community Postgres, you don't have to go via installing a whole set of libraries to make this work. If you're coming to AWS side, you don't have to install extensions on the parameter groups, which is where this is inherently built into the database. So you see the power of the database from the ground up. So if you create a trigram index, a GIN trigram index on the same example, you'll see the benefits here. So the same query with this GIN trigram index used for full text search is now down to about 15 milliseconds. Right, so this is super efficient, super quick for retrievals, super quick for lookups, and super efficient for storage as well. Because of the fact it uses, it's an inverted index, so it'll not actually store the entire storage of the index, but it'll have the key value lookups to those indexes, right? So that's the benefit. So almost at the end. So things to avoid. This is our JSON anti-pattern sort of discussion, which we tend to get in a lot. One thing I will highlight is JSON or JSONB in Postgres is definitely a very powerful capability. We've seen a lot of our sort of customers move towards those use cases, but then it's still not a full replacement for a document store. Right, it's not a document DB, it's not a MongoDB. This is not a NoSQL database in itself that can stand alone, right? So it has those capabilities that you can do to some extent, but it's not fully a NoSQL database. And if you do have requirements that you need to store like terabytes, petabytes of document in your database, consider Reddit, right? So Reddit comments, they are never going to succeed in Postgres, although they do use Postgres. It's a matter of fact. So they need these full text comments where people are expressing all sorts of sentiments about, let's say, databases, etc., or a product. Those will never fit in a Postgres data store with JSON data types. You need a NoSQL database, which is where these things are completely distinct, different. So the volume plays a critical factor. The indexing plays a critical factor. The use case is the most important, where depending on what you're trying to look up and retrieve, you'll go with the right database choice. It is also not a replacement for a full-fledged document DB or a MongoDB. So it can do a lot of things that those databases can, but it's still not really a full-fledged replacement. The other thing is size and joins. These go together. So if you talk about joins, we are not normalizing JSON-B data types, so you cannot have one-to-one relationships. You cannot have one-to-many. You cannot have foreign keys referencing each other. It becomes very complicated. Someone had a question in the previous session about the the constraints. So you basically have to now work around enforcing those constraints within JSON-B. You can create a function, yes, and then have a check or a unique constraint implemented via triggers, for example. So it becomes very complicated to maintain that referential asset compliance when it comes to JSON-B, which is where you're better off with like a full-fledged non-relational database or a document store. And the other thing is, of course, with the size we saw, these take a lot more space because these are not your fixed width or variable width data types. These are not int, these are not precision or decimal type data types. These are schema-less. So essentially, you can throw in as many key value pairs as you like. And there's really no hard limitation on storing any of this. So it can be very inefficient in terms of storage, in terms of the way Postgres will store data is 8 KB pages. So if you're falling over from one page to the other, depending on your fill factor and all the optimizations that you put in, chances are your single document is actually spilled over multiple pages. Thereby, it's defragmented or it's fragmented, and you are just taking a lot of space to access those pages on the disk, thereby just degrading your performance, right? So a lot of those factors come in. Of course, you have purpose-built databases just for that need. And that's basically the messaging. We looked at a lot of these JSON in a very introductory format today, but hopefully this was useful. We covered JSON basics. We covered the evolution coming from all the way up to from 9.2 all the way up to now. We also saw some examples of how to work with JSON data. Performance and indexing is where it's very critical to keep in mind that JSON-B is really, really awesome with indexing, more so with GIN indexes. And of course, we looked at some anti-patterns. Just last minute closing thoughts. This is where, at least at AWS, we tend to go with this sort of mental model on you have basically this problem or basically this hammer, and you're trying to solve all your problems with that single hammer, which of course can work to some extent. But when you're talking about that scale of systems, you're talking about like infinite scale, that's where things tend to fall apart. That's where we have this purpose-built sort of database story or purpose-built mental model, or the way to think about things is if you have specific use cases for a full-fledged document, yes, a document store will always do better than a relational database. If you have a time series use case where you need to do analytics on really fast-moving windows of time series database is the right choice. If you have, of course, rows and columns, age-old way of storing data, your relational database is there, was there, and will be there, right, forever. You have your in-memory cache operations. You do a lot of in-memory lookups, etc. Your data sets are cached. You do these analytic queries on your relational databases where you combine OLTP and OLAP with what we today see with HTAP data stores. You have in-memory databases, right? There's a full-fledged functionality that those databases can provide that relational just can't. And it'll take years to build that functionality in those. So similar to that, hopefully this was helpful. This is sort of, again, just a beginner journey into JSON and JSONB. And if I see you again next time, I will bring some more advanced concepts for JSON. Thank you again for your time. I know this is the end of the day, but I'll be around for any questions. Any questions? Yeah. Right. Yeah. All right. So the question is, the examples that we saw today were more around lookups and retrieval. And is there any way to update in place, if I get that right? Update in place values versus replacing, as is today, is replacing the entire document to update it. I'm not sure, to be honest. I don't know if Robert, you know. The answer is no.
I guess so the issue is actually at the storage level. So when you store the row, which is whichever field types you would have, right? So Postgres is always writing that whole row on any kind of update. So even, I don't know if you saw the array talk, like he showed there's a syntax for you can update a value in a column that's like a text array, and you can either update the whole array or you can update an individual element within the array. But in either case, what you're actually doing is rewriting the entire row at the storage layer. So what you essentially would have to do is write a new storage mechanism, right? So possibly a whole new table storage type that would understand, hey, this is a specific element in a specific location within the row that is stored on disk. So that is a non-insignificant amount of work that so far nobody seems like they want to take it on. And that is one of the things, as he was talking about, like, how do you evaluate relational versus document store? Like, that actually is a particular one that I would say if you are doing specific things like that, you may hit that wall in Postgres. And I don't see anyone like super excited about like, hey, you know, oh, we just need to change the storage on disk format, you know, and then it'll be fine. It's like, okay, that's great, but that's, yeah, nobody seems excited about taking that project on.
All right, there was another question. Yeah. So the way you saw the array examples, I don't know if you saw it in the previous one. Yeah. Yep. So the similar functions exist with JSON as well, where you can pivot rows into columns, columns into rows. And I'm forgetting the operator class, but JSONB path ops or ops, one of those supports that. So just for like purposes of reiterating, the question was, is there any way to transpose the document? Let's say we are just starting out from scratch with an application that has a lot of document style data that needs to be stored in your relational database. Is there a way to easily unpack or unnest or transpose those into specific rows and columns? And yes, the answer is yes. There are specific functions within those operator classes that do that, yes. Those are native. Those are natively available with JSONB, yes. Yeah. It'll just error out. It just errors out. It'll say something like index not found. I could have just showed it, but it'll just error out. Yeah. 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 It doesn't show you any sort of a null, or it doesn't misrepresent anything there. So it'll error out, and if from the application side, you'll have to have that retry logic to kind of find the right element. Yes. So, and it starts with a 0. So remember the 0 starting position for a JSON array. Yeah. Yep. It's a good question. Yeah. Ah. Got it. I'll have to look at that. Okay. Yeah, I'm not sure. But yeah, any other questions? All right, I think it's a wrap. Thank you everyone for your time, and looking forward to see everyone tomorrow for another exciting lineup of sessions. Thank you.